Okay, so welcome to our first project. There are 4 questions here. The first 2 basically deal with how imprecise the English language is, how easy it is to be misdirected, perhaps even form a prejudice about the question, that is, a belief that you know how the question's going to end before you've thought about it. And then 2 questions that are more mathematical in nature. So just to get us kind of throw off the summer and get back into thinking mathematically. So the first question says, the brother of the chief executive officer, the CEO of a major industrial firm died. The man who died had no brother. And then it asks, how is this possible? Now, when I ask this in a class of 30 or 40 people, I get maybe 3 or 4 hands, folks who can see how this happens. But let's see what's happening to those folks who can't see a way through this problem. There's a lot about this problem that prejudices your way of thinking. The first of those is the 2 uses of the word brother. There's a man mentioned, and then something that really pushes our mind in a particular direction, at least in our society, is the CEO, the chief executive officer. So this question does have an answer. It's obvious when you think about it. The way you can think about this is brother is not transitive. In other words, it doesn't mean that the other person is a brother. So that's certainly one way to think about it. Feel free to talk to folks about this. I encourage my students in class to talk to each other, talk to your family. When you've seen it, it's almost impossible to believe that it's hard for people to see the answer to this, unless you're maybe a psychology or a sociology major. But it really does point out how we go into a problem expecting to know what the answer will be even before we've thought about it. And often that completely throws us in the wrong direction. So kind of check prejudices at the door when you enter a mathematics class. There's all sorts of possibilities and all sorts of wonderful ways that we can see the world. So think about that question in the homework when you get in to do this project in My Open Math. You're going to see that it's the exact same question, and I accept a lot of different answers that have that same characteristic for what the CEO has to be. And again, I will say this, there is an answer. Someone in your family will get this fast. If you haven't gotten it yet, do not give up. Someone will get it fast, and as soon as they've gotten it, you'll say, how could I not have seen that? But it is important to think about things, so give yourself a little time to think about this. This second question is a perfect example of how imprecise the English language is. It's just so astonishingly imprecise at times. Really, when we read English, when we hear English, we interpret it to make it make sense to us. And this question's a perfect example of that. It says some months have 30 days and some have 31 days. How many months have 28 days? Now I'm looking at a calendar for August, and I see, August 28th, and then I see the 29th, the 30th, and the 31st. Now, if you look at a calendar and you find a month with 28 days and you don't find any others, you might say, well, that's probably what the person asking this question meant. Instead of simply saying how many months have 28 days, we interpret it to mean how many months have exactly 28 days. And if this was in a math setting, if we were doing this mathematically with symbols and all of that, we would say exactly if that's what we were interested in asking. But notice this question does not have the word exactly in it. In English, we often have to interpret things so that they make sense, kind of second-guessing the person asking the questions. But in mathematics, we have to answer the question as written. So let me rephrase this from days to shopping. Say you've got $10 in your wallet. You go into a store and there's something for $5. And you ask yourself, do I have enough money? And of course the answer is yes. You've got $10. The thing only cost $5. You've got plenty with tax and packaging and whatever else. All kind of obvious in one setting. But now look at a calendar of August again. I see August 28th. I see the 29th, the 30th, and the 31st. So I want you to interpret this question without inserting the word exactly. If you've got $10, you can buy something worth $5. If you've got 31 days, as August does, you might say, well, you've also got 28 days. So I want you to interpret that in that way. And this is another question that in your homework, when you get into the project, it will be exactly as written. The next two problems are a little bit more thoughtful. There's a little bit more arithmetic going on. So question number 3 says, a lily pad grows so that each day it doubles its size. Now the emphasis here is clearly on the word doubles. The next sentence says, on the 20th day of its life, it completely covers a pond. Then finally it asks, on which day did it cover half the pond? Now it's really easy to look at the word half and the number 20 and just take half of 20 and say 10 days and not give it nearly as much thought. We've all learned over the last few months how important it is to understand exponential growth. So let's go back to that first sentence. When something doubles in a fixed amount of time, each day it doubles its size, that's exponential growth. That means there's a constant growth rate and a constant doubling time. For this question, the doubling time is 1 day. So what that means is that each day, as you go into the future, it gets twice as big. But that's not what it's asking us for. That question is asking us to go back in time from the 20th day to the day that it covered only half the pond. Now, working backwards or undoing is algebra. Algebra literally means the art of restoring, and you can think of restoring as putting something back into the state that it was in the past. So we're being asked to work backwards, to go back in time, to start on that 20th day and go backwards. So let me ask you this. What does it mean to undouble? So to double means to multiply by 2, and you're probably saying to the computer right now, divide by 2, and that's exactly right. And when we go into the future one day, the size is increased by multiplying by 2. When we go into the past one day, the size is decreased by dividing by 2. So on the 20th day, it covered the entire pond. At this point, you can see exactly what happens. On the previous day, it only covered half the pond. Now, this is exponential growth. As I've said, it has a constant doubling time and therefore has a constant growth rate. This is, and I'm about to mention COVID-19, this is exactly why people are so concerned about the spread of a virus. If you have a constant doubling time, then instead of imagining a lily pad on a pond, we'd imagine the portion of a population that has a disease. If it took 19 days for that lily pad to cover half the pond, then you might say it's going to take another 19 days to cover the other half of the pond, but that's not true at all. It takes 1 day to grow as much as it grew in all the previous days combined. And that is a very, very insightful look at the power of mathematics. Exponential growth, exponential decay are powerful. So of course the answer to this question is on the previous day, which in this case was the 19th day. The way I've coded this question in your homework, it's not going to necessarily tell you that it took 20 days to cover the pond. It'll make up some other number, but it will say that it doubles in size each day. So you can use the same trick to say, okay, the previous day, it'll be half the size. Now, interestingly, the 18th day, it was a quarter the size, half of a half. The day before that, the 17th day, it was a half of a half of a half, or an eighth. So you can continue if you wanted to, but in the homework I'll ask you when it covered half the pond. This last question is from antiquity. It's a question known to the Greeks. It says, a frog is at the bottom of a 20-foot well. Each day the frog crawls up 4 feet, but each night the frog slips back 3 feet. After how many days will the frog reach the top of the well? When I'm teaching this in class, the first thing I ask my students is to tell me, raise your hand if you think the frog will ever get out. Now, that's a very different question than what day, which is what we're asked. how long until the frog gets out? We're assuming that, water and food aren't an issue for this frog, that if it's making progress, if it gets out, then that is good enough for it. And I hope you can convince yourself that the frog will get out, and for the obvious reason that it's climbing up 4 but only slipping back down 3. So you can quickly convince yourself that it's gaining about a foot a day. And if it's gaining a foot a day and the well's 20 feet deep, then it's going to get out. Now, the moment that we've decided that there is an end to this, we've kind of made this problem like the previous one. Instead of working forward from the first day and night in the well and all the way up to the last, we can work backwards. Again, we can think algebraically. Now, what does that mean in this context? Now, it's easy to say that the frog will be out of the well after 20 days. Now, that is not say that it took 20 days to get out, just to say that after 20 days the frog is out, assuming the frog says, I'm not going to fall down that well again. So that is something I think we can all agree on as well. There is an end here, right? This will, in computer science vocabulary, it'll terminate. There's an end to it. Last day in the well. So let's use that and let's think in reverse. So there's another peculiarity of English going on here, and that is the usage of the word day. So sometimes when we say day, we mean the 24 hours from midnight to midnight. Sometimes when we say day, we mean from morning until sometime in the evening around sunset, when night starts. And both of those words are being used here. How many days? We're not counting nights. And then, of course, we make that distinction between crawling up 4 feet during the day and then slipping back 3 feet at night. So let's make that clear, that if you climb up 4 feet during the day, the slipping back hasn't happened yet. So if we've all agreed that there is a last night in the well, let's ask ourselves what happens on the last day. So the last day, the frog climbs or crawls up 4 feet. Now, what if it makes it to the top? Well, then the frog is out. There is no night for that day, if you see what I mean. The 4 feet that the frog climbed can be kept. The frog hops away and the night never comes for it to slip back down. And the moment you interpret these days and nights in that way and kind of see them as two separate things, then you can say to yourself that the last day that the frog is in the well, the frog doesn't simply climb 1 feet and then have to climb another foot the next day. The frog actually climbs 4 feet. So now let's go back to the last night in the well. The last night in the well, the frog is not at 19 feet. The frog is 4 feet below the top of the well. The frog is at 16 feet. So 16 feet, and then one more day, and the frog is out. So then the question becomes, how many days does it take to get to 16 feet? And then, of course, up 4, down 3 tells you that you gain a foot a day. So that took 16 days. One more for that last 4 feet to crawl out. And we've got 16 plus 1 is 17 feet. This is, or 17 days. This is another one that I have coded so that it makes up different numbers. So that's why I'm showing you the answer to this one. So the depth of the well will be different in the one that you see. And then, of course, the amount that it climbs up and slips back down will be different as well. But you can use this exact reasoning to see that the last day, there is only crawling up because that night doesn't come for it to slip back down. I hope you enjoy these. I hope that they get you back into thinking mathematically, thinking about how to use English a little bit more precisely, about how to think about growth and decay, all things that we'll be interested in this semester. So thanks so much. Good luck with the projects.